Greetings, organickers. We've been working on chirality and chiral molecules. We said that the most common feature to impart chirality to a molecule is a tetrahedral stereocenter, or a tetrahedral carbon with 4 different groups attached to it. So I'm showing you here a pair of enantiomers. When we name molecules that have stereocenters, we have to indicate which enantiomer we're talking about in order for the name to be really complete. I use something that we call stereochemical descriptors, which will indicate to you which enantiomer I have. In this video, I want to describe for you how we determine absolute configuration of a stereocenter. We apply something called the Cahn, Ingold, and Prelog convention for naming stereocenters. Let me describe that process for you. The first thing that we're going to do is assign priorities to the 4 groups that are attached to the tetrahedral carbon. And just for the sake of demonstration, let's say that red has the highest priority, followed by blue, green, and orange. So I'm going to give them numbers. The highest priority, I give the lowest number, which is red, number 1, the lowest priority group, number 4. Why we give the highest priority group the lowest number, I really can't explain to you, but that's just how we do it. So let's label the groups on our tetrahedral stereocenter. Red is 1, blue is 2, green is 3, and orange is 4. And let's label the enantiomer as well. In the Cahn-Ingold-Prelog convention, I have to orient these 4 groups in such a way that the lowest priority group, or number 4, is pointing away from me. And you can see that I have both of these enantiomers oriented in that direction. The next thing that I'm going to do is I'm going to trace a path from the highest priority group to the second priority group and to the third priority group. So from 1 to 2 to 3. For the enantiomer on the left, that pathway goes clockwise, whereas for the enantiomer on the right, that pathway goes counterclockwise. When my path from highest to lowest priority goes clockwise, I call that the R isomer. R is for the Latin word rectus, to the right. When my path from highest priority to lowest priority goes counterclockwise, I call that the S isomer. S is from the Latin sinister, which means to the left. You've seen how we determine absolute configuration, but how do we assign these priorities? Well, there are really 3 different kinds of situations you're going to be faced with when you're assigning priorities. And the first thing that we do is we look at the atomic number of the atom that's directly bonded to the tetrahedral stereocenter. The atom with the highest atomic number is going to be the highest priority. If you find yourself in a situation where you have 2 or more of the same atoms directly attached to the tetrahedral carbon, you're going to have to move out along the chain until you find the first point of difference. When groups contain multiple bonds, you're going to treat those like you have multiple atoms. That's a little bit confusing, and we're going to see some examples of all of these situations. Let's look at this most straightforward situation first, where you have 4 different atoms attached directly to the tetrahedral carbon. So if I look at my 4 groups, I have hydrogen, chlorine, I have a hydroxyl group, and I have a CH3 or a methyl group. Or in other words, a carbon attached directly to the tetrahedral carbon. Hydrogen has the lowest atomic number of all of the elements. So if you see a hydrogen, that's always going to be your lowest priority group. Now I need to compare carbon, chlorine, and oxygen. Chlorine has the highest priority of those 3. Let's start to label our groups. Hydrogen is last, chlorine is first. Now I compare carbon to oxygen. Oxygen has a higher priority than carbon. So I've labeled all of my groups. My lowest priority group, which is hydrogen, is oriented away from me, so I'm looking at the stereocenter from the right direction. Now I need to trace the path from my highest priority group to my lowest priority group, from 1 to 2 to 3. That pathway in this instance goes counterclockwise, so this stereocenter has the S configuration. What if I find myself in a situation where I have the same atom bound directly to the tetrahedral carbon? Then I'm going to have to move out the chain. Here we have an example. This molecule has a tetrahedral stereocenter. This molecule is 2-butanol, or I could also call it sec-butanol. I want to remind you that we're looking at a skeletal representation, and I don't have to show you all of the hydrogens, and I'm not showing them all. However, if you see a situation where you have 2 bonds lying in the plane and one coming towards you and nothing else is showing, the 4th atom attached to this carbon has to be a hydrogen, and it has to be going away from you. Now I need to decide on the priorities of my groups. Hydrogen is going to be the lowest priority. I've already told you that. Oxygen is going to be the highest priority. I have to compare 2 carbons. Let's have a closer look. I have 2 carbons directly attached to the tetrahedral stereocenter. I need to work my way out the chain until I find the first point of difference. Looking at the carbon on the right, it's attached only to hydrogens, but the carbon on the left is attached to another carbon. So the group on the left is going to have a higher priority than the group on the right. Now I'm going to trace my path from high to low, or from 1 to 2 to 3. That path goes counterclockwise. So again, this stereoisomer has the S configuration. In the examples that I've shown you, I've oriented the hydrogen in the right direction, or in other words, it was pointing away from you. I don't always have to draw the molecule in that orientation. And in those situations, you're going to have to imagine what the groups look like when you're looking at the molecule from the opposite direction of the lowest priority group. So I want you to have a look at this and imagine what this eyeball here is seeing. Go ahead and pause for a minute and draw what that would look like. So hopefully this is what you came up with. Hydrogen is facing away from me, and now we need to assign priorities to these 3 groups. Oxygen is number 1, my ethyl group would be number 2, my methyl group would be number 3. My path is going clockwise, so this would be the R isomer. Or in other words, I can call this R2-butanol. Now let's look at some situations where we have multiple bonds. Here I have a carbon that is double bonded to an oxygen. So I imagine that that carbon is actually bound to 2 oxygens. In terms of the oxygen, since I have a double bond to the carbon, I imagine that that oxygen is bound to 2 carbons. How about this C triple bond N? Since I have a triple bond from this carbon to this nitrogen, I imagine that this carbon is bound to 3 nitrogens, and I imagine that the nitrogen is bound to 3 carbons. Let's have a look at a few more examples. Go ahead and see if you can determine absolute configuration for these molecules here. Go ahead and pause and see what you come up with. Let's have a look at this one. We label our groups. Hydrogen is the lowest priority group, bromine highest, followed by chlorine, followed by the carbon. In this case, we only have to compare the first atom that's attached directly to the tetrahedral carbon because they're all different. My path is going from bromine to chlorine to the methyl group. It's going in the counterclockwise direction, so this would have the S configuration. In the upper right, I have a molecule that has a hydrogen and a deuterium. That's what that D is. That's a deuterium. You haven't seen that before. Deuterium is an isotope of hydrogen. And when you have an isotope, the isotope that has the highest atomic mass will have the higher priority of the 2. So again, hydrogen is the lowest. Among the 3 remaining groups, my fluorine is the highest, followed by the CH3, followed by the deuterium. Here's my priorities of my groups. My hydrogen is oriented away from me, so I'm looking in the right direction. If I trace my path from 1 to 2 to 3, it is going in the clockwise direction, so this would be the R isomer. In this molecule, you can automatically see that hydrogen will be the lowest priority group, chlorine will be the highest priority group. Now I have to compare these 2 alkyl groups. So I look at the first atom that's directly attached, and in both cases it's a carbon. Now I have to start moving my way out the chain. So I look at the next carbon. This carbon on the top has 2 carbons and a hydrogen attached, whereas this carbon on the bottom has 2 hydrogens and a carbon attached. So the group on the top, or the isobutyl group, will have a higher priority than the butyl group. So here's my list of priorities. If I trace the path from high to low, it is going counterclockwise, so this would be the S isomer. In the bottom right, we have a situation where we have some multiple bonds, but we really don't have to think about those multiple bonds at all. For instance, among the 3 groups, the atom directly attached to the tetrahedral carbon is a carbon. I have to work my way out the chain. Here we have an oxygen compared to a nitrogen compared to a carbon. So the oxygen will have the highest priority, followed by the nitrogen, followed by the carbon. So here's my priorities of my groups. My path from high to low, or from 1 to 2 to 3, is going clockwise. So this isomer has the R configuration. These 2 examples on the top are a little bit tricky. My hydrogen, my lowest priority group, is oriented away from me. I can see that my next lowest priority group is going to be this methyl group, and I have to compare the 2 remaining groups. If I look at the first atom directly attached, in each case it's going to be a carbon. This carbon is attached to a carbon and an oxygen. This carbon is also attached to a carbon and an oxygen. Now I need to move out along the chain and find the first point of difference. But along which chain do I move? Well, it turns out I have to move along the chain of the highest priority atoms, so I'm going to go in the direction of the oxygens. This oxygen is attached to a hydrogen. The other oxygen is attached to a carbon. So this group is going to have a higher priority than the other group. So here's my priorities of my 4 groups. My path from high to low goes in the counterclockwise direction, so this isomer has the S configuration. The next example in the upper right, also a little bit tricky. My hydrogen, or my lowest priority group, is pointing away from me. My methyl group is going to be the next lowest, and I have to compare the 2 remaining groups here. Carbon versus carbon. I need to keep moving. If I move along the highest priority atom, I have oxygen versus oxygen, and if I keep going out, I have carbon versus carbon. Those 2 groups are the same. So in this case, I cannot take the path of the highest priority atom because the 2 groups are identical. Now I have to move along the path of the alkyl groups. So I'm going to compare these 2 carbons. This one is attached to 3 hydrogens as I move out. This one is attached to 2 hydrogens and a carbon. So here's my priorities for my groups. My path from high to low is going clockwise, so this isomer has the R configuration. See if you can determine absolute configuration of the 2 compounds on the bottom. Go ahead and pause and see what you come up with. Well, let's see how you did. Here's our priorities of our groups. Our ethylene group is going to have a higher priority than the ethyl group. My path goes in the counterclockwise direction, so this is S. In this final example, I'm comparing an ethynyl versus an ethenol versus an isopropyl group. If I look at the first carbon that's directly attached, I imagine that this carbon has 3 carbons attached to it. This carbon, I imagine, has 2 carbons and a hydrogen attached to it. This carbon also has 2 carbons, they're real carbons this time, and a hydrogen attached. So I can decide on the highest priority, and that's going to be my ethynyl group. In order to prioritize the remaining 2, I'm going to have to move out further along the chain. If I move to the next carbon of the ethynyl group, that carbon, we imagine, is attached to 2 carbons and 2 hydrogens. If I move out along the isopropyl group, either direction that I go is going to be the same. I have a methyl group. That carbon is attached to 1 carbon and 3 hydrogens. My ethene, my double bond, is going to have a higher priority than my isopropyl group. My path from high to low goes in the counterclockwise direction. This isomer has the S configuration.